Hello and welcome to Infinite Series. So first off, what is an infinite series? An infinite series is an infinite sum of the form the sum from n equals 1 to infinity of a sub n, where the a sub n's form a sequence. So essentially, it's the sum of all terms of the sequence. So the question is essentially, how do we find an infinite sum? So it turns out in order to find an infinite sum, we will use something called a partial sum. The definition, the nth partial sum of an infinite series the sum from n equals 1 to infinity of a sub n is defined as, so the nth partial sum is defined as S sub capital N or S sub n as equal to the sum from n equals 1 to capital N of a sub n. So essentially, it's the sum up through the nth term. And it turns out that we will use this to define our infinite series. So essentially, we can view the infinite sum, the sum from n equals 1 to infinity of a sub n, as the limit as our capital N goes to infinity of our partial sums S sub n. So in other words, the limit as n goes to infinity of the sum from lowercase n equals 1 to capital N of a sub n. So we can use the limit of our partial sums to then define or whether or not the limit exists to then go from there. So, to define our limit. So we say that the sum from n equals 1 to infinity, a sub n converges if the sequence of partial sums converges. So if the limit as n goes to infinity of our S sub n exists and is finite. So in other words, if the sequence of our partial sums converges. Otherwise, we say the series diverges. So just like with limits and with sequences, right? If the limit doesn't exist, then it diverges. So furthermore, if the sum from n equals 1 to infinity of a sub n converges, we say it converges to the limit as n goes to infinity of our partial sums. So here are a couple of examples. First up, show that the following series diverges. So we are looking at the sum from n equals 1 to infinity of n's. So if we just write this out, this is essentially 1 plus 2 plus 3 plus 4 plus going on forever. And we can see that we are definitely going to be, we're adding larger and larger numbers. It will go to infinity, right? But we can be more formal with this. So more formally, if we want to take our partial sums, S sub n is the sum 1 plus 2 plus 3 plus, we keep going, up to n minus 1 plus n. We can pull a little trick here. Note that 1 and n both average to n plus 1 over 2. 2 and n minus 1 also average to n plus 1 over 2. And then if there are an odd number of terms, the middle term will be precisely n plus 1 over 2. So it turns out that the overall average is n plus 1 over 2. And so we have n terms times the average of n plus 1 over 2. We wind up getting then that our infinite sum is n times n plus 1 over 2. N copies of n plus 1 over 2. So we have that the limit as n goes to infinity of S sub n is the limit, I apologize for the noise in the background if you can hear it, is the limit as, I just realized I used lowercase n's here, so I'll stick with that. So we have the limit as n goes to infinity of S sub n as the limit as n goes to infinity of n times n plus 1 over 2. And that, of course, is infinity. And so we have it diverges. So this is the more sort of formal rule. In general, this may be of use later. So in general, if we have no, let's not do that this time around. You can play this same trick that I used here in various cases where you have sums, as long as the distance between each number is the same. So to get from 1 to 2, we add 1, to get from 2 to 3, we add 1, etc. You can play a similar trick to this. All right, so in that case, we do have divergent. Now here we're going to take a look at a series that actually converges and figure out what it converges to. So here we have the sum from n equals 1 to infinity of 1/3 to the n. So here we're essentially looking at 1/3 plus 1/3 squared plus 1/3 cubed plus going on forever. This is not so obvious. We're adding smaller and smaller and smaller numbers. It may converge, it may not. But if we actually look at Sn would be 1/3 plus 1/3 squared plus 1/3 cubed plus all the way up to 1/3 to the n. Now we have a little rule. Note that if we have 1 plus x squared plus all the way up to x to the n minus 1, this is the same thing as x to the n minus 1 divided by x minus 1. So what we are going to do is we are going to manipulate S sub n into this format. So we can manipulate S sub n into this format. And the way that we will do so is we can pull out a 1/3. So S sub n is equal to 1/3 times 1 plus 1/3 plus 1/3 squared plus all the way up to 1/3 to the n minus 1. This, of course, can be rewritten as 1/3 times 1 plus 1/3 plus 1/3 squared plus all the way up to plus 1/3 raised to the n minus 1. So essentially here, x is our 1/3. We can use our formula from above. So fits 1 plus x squared plus all the way up to x to the n minus 1 with x equaling 1/3. So this is equal to, we have our 1/3 out front, then we would multiply by, we have x to the n minus 1. So we have 1/3 raised to the n minus 1. And then all over x minus 1. So 1/3 minus 1. I'm going to go ahead and flip both the top and the bottom as 1/3 times a negative, and then in parentheses, 1 minus 1/3 to the n over a negative, in parentheses, 1 minus 1/3. So we have 1/3 times 1 minus 1/3 raised to the n divided by 1 minus 1/3 is 2/3. And so this becomes 1/3 times 3/2, or 1/2 times 1 minus 1/3 to the n. At this point, if we take the limit as n goes to infinity of S sub n, This is the same thing as taking the limit as n goes to infinity of 1/2 times 1 minus 1/3 raised to the n. As n goes to infinity, that 1/3 raised to the n goes to 0. And so we just wind up with 1/2. So what we get is that the sum from n equals 1 to infinity of 1/3 to the n converges to 1/2. So in the next videos, we will learn some tricks for checking for convergence, as well as some shortcuts or formulas for series that look similar to this last one we just did. But this is sort of the basics of how we can find convergence and divergence. As long as we can find a formula for our partial sum, we can then evaluate the limit.